We have a really remarkable group of speakers. Each of them will have 12 minutes to talk, and then they'll have 3 minutes for questions from you who are here, as well as questions from people who are attending virtually. And my plan, frankly, is just to cede my time to them to make sure that you get to hear them talk as much as possible. And just so you know, this is the Rehabilitation and Physically Assistive Systems keynote session. And with that, I will give the floor.
Thank you, Charlie. So my lab is located inside of a rehabilitation hospital. It's called the Shirley Ryan Ability Lab, and this is an open plan hospital that fully integrates clinical practice with research. So my engineering students are writing code to run on our robots literally steps away from inpatients who are receiving physical therapy. Across the field of rehabilitation, we use assistive machines to bridge gaps in human function. And there's a persistent challenge in how to capture control signals from bodies with motor limitations in order to control these machines. On the right, we see interfaces that are available at increasingly high levels of spinal cord injury, and as we go from the bottom to the top, these interfaces lower in dimensionality, and they go from issuing continuous control signals to discrete ones. So trying to use a sip and puff at the top, which issues 1D discrete signals to operate a powered wheelchair, already is a challenge. And that challenge is just exacerbated as you go to more complex machines that require higher dimensional control signals. So just positioning the end effector of a robotic arm is now a 6D control problem, and none of these interfaces fully cover that control space. So to recap some of the challenges of assistive machine operation, we have the human impairment, which is actually masking and filtering the control information that the human would like to transmit to the machine. We have limitations on the dimensionality and continuity of the control interfaces that are accessible to people with severe motor limitations. And we have this catch-22 of machine complexity. So within the field, for quite some time now, researchers have been exploring introducing autonomy to these machines in order to offload some of the control burden from the human to the robotics autonomy. So to do this, sensors are added and intelligence is added to reason about that sensor information as well as information coming from the human. So if we take a step back and look at the field of rehabilitation robotics more broadly, I tend to think of rehabilitation robots in two big bins. One is robots that rehabilitate the human body. So this Locomat is actually guiding the human limb through rehabilitation exercises. The second are robots that replace lost function, for example, a prosthesis. And when we think about adding autonomy to these machines, a big differentiator is whether or not the robot is worn on the body or not worn on the body. And the reason why is because we are adding those sensors, adding that compute, and it needs somewhere to go. If you are just tossing it onto a powered wheelchair, drawing from the wheelchair's batteries, no problem. If you are now embedding it within an upper limb prosthesis that already has a somewhat tenuous socket connection with the human arm, it is an entirely different human engineering integration question. So my lab has been working in the field of adding autonomy to assistive machines for over a decade. Our early work really focused on the question of how control should be shared between the autonomy and the human. And time and again, the theme emerged where we saw humans were very variable in how they wanted to interact with this autonomy. They were variable in how they wanted to interact with the autonomy, and they also were quite variable in how they were able to issue control signals to the machine. So this has led to a newer line of research in my lab where we are trying to mine as much information as we can from those limited control signals that we are able to get. So here is sort of a typical model of teleoperation. We have a high-level task-level action that the human would like the robot to do, like move forward, and then the human selects a control command to achieve that, such as a forward velocity. And we would argue that this framing is user interface agnostic. And what is not captured by this model is the fact that for the human to issue a control command, they need to actuate an interface. Doesn't matter if it's a button press, if it's a joystick deflection, if it's electrical signals from their brain that are being captured by a BCI, they need to do something with their body. And the interface measures that thing that they do. Moreover, there can be discrepancies between the interface command that they intended to issue and what actually got measured by the interface. So we have been trying to build more complete models of robot teleoperation that do take into consideration interface awareness. And our current framing has gotten to the point where we are able to build specific models, or models of specific humans operating specific interfaces that don't require any knowledge of the task, don't require any knowledge of the human's control policy or of the environment. And yet, somewhat surprisingly, we are able to do as good of a job at reducing the number of number of collisions as a controller that does have access to environment information and is explicitly trying to avoid obstacles. So we're quite encouraged by what this might mean for our end users. Okay, but my lab has continued to do its more bread and butter work of robotic wheelchairs as well. Currently, we have a project under the National Science Foundation's Convergence Accelerator program where we are trying to address barriers to independent mobility. We have a lot of partners on this project, as is the convergent research mandate of this program. So for example, my co-PI is the CTO of a company called Lucy. We have team members who are clinicians, and we also have team members who are end users. And I want to take a moment to talk about Kevin Rowland. So he is an engineer and a computer scientist, and he's living with ALS. And his ALS has progressed to a point where he uses his eyes to communicate with the world through an eye-gaze interface. So he uses his eyes to speak, he uses his eyes to drive his powered wheelchair, he uses his eyes to write code for our project, which is pretty remarkable. So on this project, we have 3 main technical thrusts that we are pursuing, and I'm going to zoom in just on one of them for the moment, and this is the robotics intelligence that we are adding to the wheelchair driving. So Lucy is already a commercial product. It's a sensor, it's a retrofit to existing powered wheelchairs that adds on sensing, adds on compute, and what it will do is it'll detect obstacles in the environment, and it'll detect drop-offs, and it will slow or stop the wheelchair in response to those dangers. What we are doing is expanding the capabilities of Lucy's assistance to do things like actively drive around obstacles. And we are on track to push out the first of this work within the Lucy product by the end of this calendar year. Okay, so the final project that I'd like to talk about, in this project, the Robotics Autonomy plays a different sort of role. The role it plays is actually in helping to train the human user in how to operate an assistive machine. And I'd like to talk about this project from the perspective of its evolution along multiple dimensions. So where this project started was that Sandro Musavaldi, my collaborator, had been developing for years this idea of a body-machine interface. He had been focusing in particular on putting sensors, IMUs, on the upper body of people with cervical-level spinal cord injury. So they have very subtle movements left in their upper arms and shoulders. And he would project these sensor readings down to a 2D control point and be able to do things like control a powered wheelchair or control a cursor on a screen. What we wanted to do was project this to a higher dimensional control point, specifically so that we could operate a robotic arm in 6 dimensions. Because if we could do that, we no longer needed to mode switch in order to access the subsets of the control that were not accessible with the control interface. We knew that this would be hard to access 6 independent control axes, especially from people with motor impairments. And so our idea was to use robotics autonomy to help, and that we would progressively scale back the amount of assistance from the autonomy and the number of control dimensions that the autonomy was contributing to in order to assist with human motor learning. So we started out with a baseline study. This study had no phased learning, it had no robotics autonomy, it had people without any motor impairments, and they came in for 5 sessions each. And what we wanted to just see is open-ended. If someone comes in for 5 consecutive days, can they learn the system, at least to a certain extent? They could, to a certain extent. So our next step was to perform a scoping study, and this was to assess the movement range of our spinal cord injured end users who were the target. Based on this, we came up with a fitting protocol on where to place the IMU sensors and which motion prompts to guide someone to issue in order to issue this 6D control signal. We had our machine learning map that would map the IMU signals over to the 6 control dimensions of the robot, and then we built out the rest of our pipeline. So we have a 6D task, GUI task that's on a screen, and we also have multiple robot reaching tasks with the robot hardware. So we built out the pipeline, and then we needed to vet it. So this now was an autonomy-assisted learning protocol. It executed over 18 sessions, and we started out with 2 uninjured participants, and then we moved on to our first spinal cord injured participant. After running these participants, we realized we needed to update our hardware. Our robot arm was wearing out, and also we had far too much drift in our IMU sensors. We actually had already updated them once, we had to update them again. Okay, so after changing all the hardware, of course, we needed to vet the system again, this time with 2 spinal cord injured participants. And what we found as we ran more and more spinal cord injured participants was that our fixed protocol for fitting the body-machine interface to them was not meeting their mobility needs. or their mobility capabilities. And so what we ended up doing was coming up with a customized fitting protocol that begins with a clinical evaluation that's performed by a therapist. The therapist then comes up with a ranking, an ordered ranking of potential body motion prompts that the user could issue. And then the therapist works with the engineer to select from this list the set of prompts that we're going to use in the hopes that we will minimize crosstalk between the IMU sensors. Okay, so we had our new fitting protocol that was actually presented last week at ICRA. And then we also had to update our actual study protocol, so the progression of our study sessions and what role the robotics autonomy was playing in those sessions. There were a number of reasons for doing this, and we made a number of changes. I don't have the time to go through all of them, but I will highlight that one of the reasons we had was that we had a false assumption about the fact that we presumed that lower dimensional robot control would be easier than higher dimensional robot control. And the reason why that ended up being false is because teleoperating this robot arm, it is very prone to getting stuck in singularities. And it's really hard to get out of the singularities if you can't wiggle your way out in all the control dimensions. So we recast our assisted robot learning to one of it gradually unlocking control dimensions to gradually increasing the constraints on our target reaches. And so we start out with 3D constraints and we increase that gradually to 60. But the person actually has access to all 60 control dimensions should they choose to want to wiggle within them. Okay, so based on this, we had our new protocol. This is a 12-session protocol. It's phased autonomy-assisted learning. And our goal is to run 10 spinal cord injured participants through this protocol for a total of 120 sessions. To date, we have complete 8 of these participants, and we have 2 underway. We've completed 112 sessions, and we've got 8 more to go, the next of which is starting in about 2 hours. And what I'd like to highlight as sort of a final thought is that in order to get to the point where we could run this study, we actually had to go through that process of evolving our protocol. And all of the, sorry, it's a little bit hard to see, but the numbers you see on the right that are in blue, those are all of the participant sessions that are actually not going to show up in this final data set. But if we had stopped, for example, after our first vetting study, which according to the publishing standards of the field would have been totally reasonable, if we had stopped then, we would never have uncovered the fact that our fitting protocol was not meeting the needs of our end user, that our learning protocol was not actually eliciting the learning that we needed to have. So as hard as this work is to do, it's really critical to put in that tough legwork. Oops, sorry, I meant to restart the video earlier. And with that, I'd like to thank my current lab members on the left, my funding sources, and prior lab members on the right. Thank you.
Thank you very much. So we have time for questions. There's a question right there. I think the microphones are on the stands, so if you would line up behind them, and if you need the microphone to be brought to you, please hold your hand up.
Hello. Thank you for your talk. It was great. My question would be, these chest-mounted accelerometers, is that satisfactory? Like, are you satisfied with that? What are the drawbacks? What are the advantages for using sensing like that?
Yeah, so I'd say the biggest drawback is drift and finding a sensor that actually can mitigate that. We did find a company that did, so that was good. Of course, as we use these more complex sensing technologies, we have this trade-off where the interpretation of the control signal has a lot more ambiguity than, for example, a joystick deflection, but we can conform the interface to the user instead of requiring the reverse, where the user conforms to the interface, and we can potentially get richer control signals. So whether or not it's enough, I don't know. Certainly, it still has work to go. But I think that it's a complementary approach. I think for some tasks and some users, using a fixed, simple interface makes sense, and for other tasks and other users, it doesn't.
Thank you.
Hello. Thank you for this speech. I have a question regarding increasing the autonomy of robotic assistants, right? So nowadays with increases of usage of LLMs, VLMs, is it worth going the route of intention decoding? And if it's not, why not?
Yeah, I think that really is going to depend on the application and the user. You're going to have users who never want their intent decoded. They want to be in fully manual control, even if it doesn't do as good of a job. One thing we've seen with actually our interface-aware work is that people actually quite like the interface awareness, I think because it's just replacing the command that they meant to issue, because we build these models of how they make mistakes in issuing commands. That's very different than saying there's an obstacle and I think you probably wanted to go to the right, right? And in terms of inferring intent. It's inferring intent at a much lower level. So I think there's something to be considered there. Again, it depends on the task. It depends on the capabilities of the person. If they need the autonomy in order to operate the machine, period, they're going to be much more open to it. Or many people who aren't open to it when they have the capability will now become open to it. Not everyone, of course, but there are people who will fall into the category. So it's a really nuanced question, I'd say.
I see. Thank you.
You're welcome. Okay.
Thank you very much. Yes, please, thank the speaker again.